Hi everybody, welcome back. Let's talk about the second correlation example. It says, based on sample data, is there evidence that high school GPA and college GPA are related in the population? Of course, we just have sample data. We want to see if our sample data is strong enough to suggest that there's a correlation between the two variables if we were to measure everybody in the population. In other words, is the sample correlation significantly different from zero? Of course, zero would represent no relationship between the two variables. Compute a Pearson's correlation coefficient. Conduct a two-tailed test with an alpha of 0.01. So we'll use an alpha of 0.01 just to get some experience using an alpha level other than 0.05. So let's take a couple little notes here. 2, 4, 6. We have an n of 6. And remember, that's important because all of our formulas have n in it. And it's easy to look at the data and think that n equals 2, 4, 6, 8, 10, 12. And that is not correct. We do have 12 pieces of data, but we have 6 pairs of data. So we have to make sure that we're looking at that correctly because that would affect not only our formulas where we're asked for n, but also our degrees of freedom, which is based on our sample size. All right, so we've got that out of the way. We've got high school GPA and college GPA. We can call high school GPA X and college GPA Y. For this analysis, it really doesn't matter which we consider X and which we consider Y, but we usually like to have X as the predictor variable and Y as the criterion variable. And it makes sense that we're going to use high school GPA to predict something that happens later on, college GPA. All right, so let's move along to step 1. We need to state our hypotheses. Of course, our null hypothesis states no effect. And if there is no effect or no relationship between these two variables, then the population correlation, which in this case is rho, would equal 0. So rho, the population correlation between high school and college GPA, is 0. And then the alternative is that it's something other than 0. Remember, it can be positive, it can be negative. We're predicting, I assume you would agree, that the correlation between these two variables would be positive. I'm predicting that students who have a higher high school GPA are going to have a higher college GPA, and then students with a lower high school GPA will have a lower college GPA. And this is one reason why high school GPA is used to determine who's going to be admitted into a university or maybe a program within a university, because we know that we can use a person's high school GPA to predict how well they're going to do in college. And typically, universities only want students who are going to be successful in their programs. Let's move on to step 2. And in step 2, we need to locate the critical regions. We're doing a two-tailed test, so we have a critical region on the left and on the right side of that distribution. So let's go ahead and sketch a distribution. This is a distribution of all possible sample correlations. Remember, we always create this based on the null hypothesis being true, and the null hypothesis states that the population correlation between those two variables is 0. So we see that right in the middle. But remember, even if that is true, we would expect some sampling error. So we would expect to find some sample correlations that are positive or negative. We'd expect to find some variability. But it would be unlikely to find an extremely positive correlation or an extremely negative correlation just by chance. So where are those cutoff points? We know those cutoff points are based on the sample size. We have 6 pairs of data. And specifically, degrees of freedom in this situation is computed by taking n, which is 6, and subtracting 2. So we have 4 degrees of freedom. So let's go ahead and look in our R table. We know that we have an alpha level of 0.01, so we're going to use this column. We have 4 degrees of freedom, so we'll use this row. And when we come across this row, we see we converge right over here with this column. So that means our critical values will be positive and negative 0.917. I'm sure you see that's a really large number. Remember, correlations range between -1 and 1. So this is a really high value. We need a lot of evidence to reject the null hypothesis. And that makes sense because we have a high standard right here. We'd only be making type 1 errors using this decision-making process about 1% of the time over the long run. So we're going to need a lot of evidence in that regard. Plus, we only measured 6 people. And if you're going to have such a small sample size, you're going to have an underpowered research study. And when you have an underpowered research study, you need a lot of evidence, a large effect size to find a statistically significant result. All right, so that's how much evidence we need. Let's bounce back over here. So we're going to label that. And again, I have a mistake in here. You'll want to make sure that you write it correctly. Those critical regions are marked off by an R value, not a Z value, an R value of positive or negative 0.917. All right, let's move on to step 3. If step 2 was figuring out how much evidence we need, step 3 is about figuring out how much evidence we have. And what that means is go ahead and compute the test statistic. And in this case, if we're trying to find out the relationship between two variables, we know that we want to compute a Pearson correlation coefficient. So the first thing I'm going to do is look at the formula for that Pearson's R. And I see I'm going to need 3 things: sum of the products, sum of squares for the x variable, and sum of squares for the y variable. Of course, then I can look at formulas for those individual things. And then I can see what I need. I can see that I'm going to need the sum of the squared x values. I'm going to need the sum of the squared y values. I'm going to need the sum of the x's times the y's. So in addition to just the sum of x and the sum of y, which I can get just from these existing columns, I'm going to need a column for squared x values, squared y values, and x's times y's. So at some point you need to do the prep work. That's completely up to you. When we work on correlations, I just find that I've got some room to do it at step 3, and it makes sense to do it at that point. So it doesn't matter when you do it, but at this point I'm going to need to square every x value, which I do right here. I'm going to need to square every y value, which I do right here. And then I need to take the x value for each person and multiply by the y value for each person. So in this case, 1 times 1.5 equals 1.5. 1.5 times 2 equals 3. 2 times 2 equals 4, and so on. And at that point, we just have to get sums for each column. We know we need the sum of x, we know we need the sum of y, and the sum of every other column. So just go ahead and add them all up. So check your answers with mine, and you should find these sums. At this point, we just stick those sums into our equations. So let's work on one of the equations together. Let me pull out my calculator. Let's work on sum of squares for the x variable first. So we need to start with the sum of x squared. Here's our column for x squared. That sum is 41.25. So I stick it right there. Now I need to subtract this fraction. So I'm subtracting the sum of x, that quantity squared. That's 14.5 squared, which equals 210.25. And I need to divide that by n, which is 6. So let's just go ahead and do that now. We get 35.04. So I'm going to subtract that from 41.25. So let's put in 41.25 and then subtract 35.04. And that equals 6.21. And then, of course, you can work out these other two formulas on your own. So at this point, now that we have the sum of squares for x, the sum of squares for y, and the sum of the products, let's go ahead and compute R. So the sum of the products we found right here is 4.54. Sum of squares for x and y, we're going to need to multiply. So let's do that next. We'll take 6.21 and we'll multiply by 3.71. That equals about 23.04. According to our equation, we need the square root of that. So don't forget to take the square root after you multiply. So let's find the square root of 23.04. Remember, a little bit of rounding as we go is no big deal. 23.04. It just allows us to take things step by step so that everybody can understand what's going on. That equals about 4.8. So then finally, let's take that 4.54 and divide by 4.8. All right, there's our obtained correlation coefficient. Let's just look at it and see if it makes sense. First of all, it needs to be a value that ranges somewhere between -1 and 1, and this does. We were predicting, because of the two variables involved, a positive correlation, and this is a positive correlation. So that rounds off to about 0.95. That is our obtained R value. That's how much evidence we have. So now let's figure out where that is in our distribution of all possible sample correlations. We want to see if it's in our rejection zone. So we've got that value of 0.95. Remember, a value of 0 is right here in the middle. Our critical region is marked off at 0.917. And the question that we ask ourselves is 0.95 within that rejection zone? And the answer is yes, it clearly is. All right, so then we've got some follow-up questions. Should we reject the null hypothesis? Yes, we should reject the null hypothesis. If the sample correlation is inside that rejection zone, yes, it's in the rejection zone, then yes, we should reject the null hypothesis. So we're going to embrace then the alternative. Let's just take a look at it for a second and see what it tells us. It says that the population correlation between high school and college GPA is not 0. And what we can conclude is that it's a positive value. There's a positive correlation between these two factors, between these two variables. So we've learned that students who have higher high school GPAs do have higher college GPAs. Students with lower high school GPAs do have lower college GPAs. Now, this is a very strong correlation. We wouldn't find a correlation that strong in the real world between these two variables, but we would indeed find a positive correlation between these two variables. So let's keep going through our questions. We said yes, we're in the rejection zone. Yes, we reject the null hypothesis. Do we have statistically significant results? Yes, we do. Our results are statistically significant. They're very unlikely to occur just due to sampling error. Is there at least a possibility that we're making a type 1 error? Yes, there is at least a possibility. What is the probability that we're making a type 1 error? Well, if we're using an alpha level of 0.01, then theoretically speaking, the probability that we're making a type 1 error is about 1%. Let's go ahead and write up the results at step 4. Of course, we just want to summarize everything that we found. So we will say that our R value equals 0.95, and that value's inside the critical region. So here I'm laying my justification for why I'm going to reject the null hypothesis. 0.95 is within the critical region, and this is very unlikely to occur if the null hypothesis is true. It makes me question the null hypothesis, and ultimately I reject it. There is indeed a significant positive relationship between high school GPA and college GPA. So that's our interpretation in everyday language. How would this test be summarized in a journal article? Well, we computed in R value, so we'd start with R. We'd say that we have 4 degrees of freedom, and that value is equal to 0.95. And the probability of finding that result by chance was less than 1%. Remember, the R value of 0.95 is in that rejection zone. It's in that small region. If it's inside that small region, it should be associated with a small probability. It's very unlikely to occur by chance. Well, what's unlikely to occur by chance? A probability less than 0.01 or a probability greater than 0.01? If it's unlikely, if the probability is small, a smaller probability would be P, probability less than 0.01. So keep practicing that. We got to make sure we get that right every single time. And of course, that's based on a two-tailed test. Now, to compute the appropriate effect size in this situation, we would compute R squared. Remember, R squared is often known as the coefficient of determination. It's very easy to compute. We're just going to take 0.95 and square it. Let me grab my calculator again real quickly. We'll punch in 0.95 and hit the square button. So that equals about 0.90. So in this case, if R squared equals 0.90, we would interpret it this way. We can say that 90% of the variability in college GPA can be explained by high school GPA. Do you remember how we format that? Some percentage of variability in the criterion variable can be explained by the predictor variable. In this situation, that means 90% of the variability in college GPA can be explained by high school GPA. If these two variables were really related in this way, this strongly, then we'd be able to predict college GPA very accurately by knowing someone's high school GPA. In this case, in the real world, the last time I checked, the correlation was somewhere around maybe 0.25 or 0.3. It's a much more modest correlation. All right, everybody, that was example number 2. If you have any questions, make sure you reach out and talk to me or one of the tutors. We've got just a little bit more to talk about with correlation before we get to regression, and I will do that in the next video. See you then.